So we have 13.4, number 4. Let me share the screen. For some reason, my image, yeah, there we go. All right. Okay, so is this the one you're asking about?
Yeah.
13.4. Let me copy down the information here. It says use Green's theorem to evaluate the line integral of the vector field big F, which is x to the sixth comma 9x around the boundary of the parallelogram of the following figure. Note the orientation. This is important. We're told that x naught is 9 and y naught is 9. So it looks like I'm just going to draw the picture and I'll go to my overhead here. Now, first of all, do you notice that it's oriented clockwise? Everybody catch that?
Yes.
Okay. All right. So we're going to have to take that into account at the very end. We can still do the problem. All right. So here's the picture. Here's the parallelogram. We're told in this case, x naught is not, they're both 9. So this is the point 9, 9. This is 18 and 9. This is 9 and 0. This is the origin. Okay. So if we were to do a line integral directly, we would have to do 4 of them. And that just takes time. So Green's theorem allows us to do the line integral by actually performing a double integral on the interior. Okay. So I'm going to stop the share. I've got it on my overhead here. Green moment. Go. Let me pin this. The Green's theorem. I tend to use letters M and N for my vector field components. I know that in the homework you get a lot of P's and Q's and stuff like that. You've just got to keep track of them. It's actually the second component with respect to X minus the first component with respect to Y. So N sub X is, well, just 9. M sub Y, oh, we catch a break here. It's going to be 0, right? Everybody catch that?
Yeah.
So that's good news because that means we have a double integral 9 dA, and the interior, I'll just call it R over region R. Okay. Now, this is actually really good news because when you get a constant integrand, you can feed it out to the front, and then double integral dA of R is just the area of R. And well, there's the parallelogram's area is basically its base times its height. Okay, so the base is 9, the height is 9, so it's going to be 9 squared. So we got a lot of nines in this problem. So our answer is 9 cubed, which is 729. But we're not quite done. Okay. Because it was oriented clockwise, so we have to negate the answer. The orientation was clockwise. So now we just throw a negative on it, and now we are happy. We get a little happy face. Does that help?
Yeah, that helps a lot. I think I was multiplying by 2 because of the area, but I realize now I don't have to do that.
Okay. You got the Green's theorem integrand correctly. I mean, yours will probably be slightly different, but so you're able to do all that correctly.
Yeah, yeah.
Okay, good. Um, if now I'll admit we got lucky here because we got a constant integrand, so we can move that out to the front, and that means that it's just double integral dA. And then here you just use formulas from geometry. This is a parallelogram, but it's still basically going to be base times height. There's no difference. You can make this thing as extended out as you want. As long as the base is 9 and the height is 9, it's still 81. And then so this 9, the outer 9 is what you see here, and then the inner 9, that's the outer 9, and then the inner 9 is 9 squared, so 9 cubed. And there you go, you're done. And I'll just mention that if for some reason you still get a variable in your problem here, then you have to go through the process of setting up the double integral the usual way with the bounds. Okay. But otherwise, in this case, we got a little lucky. I ain't complaining. Any other questions on this one? So this is 13.4, number 5. Let me copy all this down. It's sine x plus 6y dx plus 3x plus y dy. And we want to find the line integral along this path that it looks something like this. And we're going from 0, 0 to, I guess B is 2, 2 to 2, 4 to 0, 6. And that would be oriented this way. I put the little arrows on. All right, so I'm going to stop the share. Okay. Now, again, if we're going to do a line integral directly, we have to do 3 of them because there's 3 little portions to it, and that takes time. Technically, we're not allowed to use Green's theorem here because this is not a closed object. This is just the curve actually ends here. So what if we do this? Let's close it off. Let's add a segment from 0, 6 to 0, 0. Okay. And then now that's an easy line integral to perform. And that'll take just a few moments. And then we'll use Green's to calculate the whole line integral, i.e. around all 4 sides. And then we'll calculate the line integral for this edge here. We'll use Green's to find all the entire line integral. So then the difference will just be the answer. It'll be these other 3 sides. Did everybody catch that logic? Okay.
No, can you explain it a little bit more?
Yeah, sure. So Green's theorem allows you to find line integrals around a closed curve, a curve that starts and ends at the same point, okay, by actually performing a double integral over the interior. And that's nice because usually you can do it as a single double integral as opposed to having to work out a whole bunch of separate line integrals. Um, but technically this problem doesn't quite meet the conditions for Green's theorem because it's not closed off on this edge. So we're actually going to do that. We're going to add a 4th edge and we're going to close it off. Okay, that's what we're doing right here. So we're going to close it off. We're going to add a segment from 0, 6 to 0, 0, and we're going to find its line integral. I'll do that in a moment. And then we're going to use Green's theorem to do all 4 sides essentially. And then whatever the difference is, so basically all 4 sides minus the side here is the other 3 sides. So it's kind of a sneaky way of doing 3 line integrals without having to actually perform them. Okay. Does that help?
Yep.
Let's run through this and if other questions pop up, let me know. Okay, so first of all, this is a line integral that's been spread out. It's actually the vector field would just be sine x plus 6y. Oops, I didn't mean to close it off so fast. My bad. Comma 3x plus y. Okay, that's the vector field. And as usual, I use m and n. And again, so the Green's theorem, follow the arrows, it'll be n sub x minus m sub y. So n sub x is 3. N sub y is, I'm sorry, m sub y is 6. So it's minus 6. So we get negative 3. And so eventually we're just going to do a double integral of negative 3 dA. Okay. Now, hopefully you're seeing that, hopefully you're getting a good feeling about this because that's negative 3 times the double integral dA. And we can just use geometry for that. Okay. So in fact, I'll tell you what, let's save that. Let's do this line integral here. Okay. So I need to parameterize the line segment from 0, 6 to 0, 0. All right, so that's where I have to come up with a line segment that goes from 0, 6 to 0, 0. And so I want it when t is 0, I want the point to be 0, 6. So it looks like if I do just a 0 here, that should work. And then 6 minus t here. And that'll be for the bounds t 0 to 1. I'm sorry, 6 minus 6t. Just tuck it in there. Okay. So again, let's convince ourselves this is true. When t is 0, I plug a 0 in there and I get 0, 6. That puts me right there, this point. When t is 1, I get 6 minus 6, which is 0. That puts me at the origin. That's my parameterization of this little line segment here. Then I come along and I find the derivative. Well, that's still 0. That's just going to be negative 6. All right, that's good. And then, okay, then it gets a little crazy, but it's not too bad. What we've got to do here is make the replacements up here. This is our x and this is our y. So the vector field, when we replace it with r, it's going to look like a mess just for a moment, but actually it's not too bad. When I plug in x is 0, that just drops out and I get 6. Okay. So I'm going to get sine of 0 is 0. I'm going to get 6 times 6 minus 6t. And then I'm going to get comma. Now x is 0 again. Y is just 6 minus 6t. Okay. So I'm setting up my line integral the usual way. This is the long way. Parameterizing, it's f dot dr. F is what you see right here. Dr is what you see right there. Now when I dot them, I catch a break because this 0 is just going to drop this guy out entirely. So I'm going to have negative 6 times this expression. So negative 6 times 6 minus 6t. So that becomes negative 36 plus 36t. And that's my integrand. And my bounds are 0 to 1. So it's actually a pretty easy integral. Okay, so again, I'm still working on this path here. Let's work it out. I get negative 36t plus 18t squared. Bounds are 1 and 0. When I plop in a 1, I get negative 36 plus 18 is negative 18. And 0 just drops out. So that's the answer for this line integral right here. Okay. All right. If you think this is a lot of work, it's actually not, because if we were to do this the long way, you'd be setting up 3 of these. Okay. You'd probably be at this for about a half hour. So this segment here has a line integral of negative 18. Now over here, we were doing Green's theorem on the whole interior. We had negative 3 times double integral dA. So it's negative 3 times the area of the trapezoid. And that's going to be, let's see if I remember my formula here. It's the base times the, what was it now? I just break it up into parts. This is going to be 2 by 2. This is going to be 2. This will be, I'm sorry, 4, 2, and 2. So it's going to be 8. So this negative 3 times 8 is negative 24. So that's the whole line integral of all 4 sides. The this side here is negative 18, so negative, just bring them together. Negative 24 is going to equal negative 18 plus x, and x turns out to be negative 6. So the other three sides have a sum line integral of negative 6. I'll admit that's a lot of steps, but it's actually quicker to do it this way than to work it out as separate line integrals. This is the old trick of closing it off and using greens. So this line integral from here to here to here to here is just negative 6. All right, I'll pause for questions. Any step here I can explain?
Can you show how you parameterize on the first one?
Yeah, this is just a line segment. So if I go back to like way back in module 10, you start with your initial point 0, 0.6. I'll do it off to the side. This is 0, 0.6. That's your initial point plus t. And then your direction vector, you need the vector that goes from 0, 6 to 0, 0. That's going to be 0 and negative 6. And then you just bring them together. The zeros just drop out, so you just get, well, it stays, but it's a 0. And then 6 plus negative 6t. Okay, and that's how we got this parameterization. And if you do it this way, the bounds are always 0 to 1.
Oh, okay, thank you. But is there like a way to just do kind of like the line equation where you take the slope or like the mx plus b form?
You can. The problem if you do that is that you may not get the nice bounds. See, the part of the reason of doing it this particular way of doing, like if you're given 2 points, doing endpoint minus starting point as your direction vector, is that the bounds always work out to be 0 to 1. These become your bounds of integration for line integrals. If you do it any other way, as long as you're careful, it'll work. But you have to be careful what your bounds are. You might get different bounds. You just need to make sure that when you plug in the first number, you get the initial point. When you plug in the second number, you get the ending point.
Okay, yeah, that makes sense. All right, thank you.
Sure. Any other questions on this one? There's a lot going on here. There's probably about 10 different skills being brought into play on this one problem. It's an excellent problem. So, um, I wouldn't be surprised if you see it later on, hint, hint, or something like it. Also, just as a reminder, I have a problem. It's not identical to this, but it's very similar on my website, on my notes. So if you want to see another worked out example of a similar type, go to my webpage and just bring up Green's theorem, and you'll probably find it in the various examples. All right, we got a chat 13.7, number 5. All right, so I'll do that one next. Is there any last questions on this lovely guy?
No, all good.
You're good? Okay.
Yep.
Again, if you think of one later, I can bring back the piece of paper. So, okay, so 13.7, number 5. Compute the flux of the vector field. So we want to find flux of the vector field F, which is 5y, 1, and negative 5xv to the surface S, which is the surface, it's a paraboloid topped by a disk. No, I take that back. It's just the paraboloid. So the surface is y equals x squared plus z squared. And we're told that x squared plus z squared is less than or equal to 4, so that's a circle. Okay, and oriented in the positive y direction. Okay, yeah, let me stop the share. Give me a second here. Um, there's a couple ways to, we have the parameter, we have to actually come up with the n vector that sticks up out of the surface. And we're going to kind of use a nice little shortcut. The n vector, in this case, we want to keep the y positive 1, so that means it's going to be negative f sub x and negative f sub z. Okay. This is for cases when we have an explicitly defined surface. That means one of the variables is isolated. Okay. And again, I have this in my notes. It's kind of it's a length. It takes a while to explain. You can work it out with cross products, but you'll always end up getting this feature. Okay. Um, all right. So I want to then, let's see. I want to well, obviously take the derivative. Let's do that. So it's going to be negative. It's going to be two. So negative 2x 1 negative 2z. Okay. And then we have to go to the function and actually make some substitutions here. And so let's come back up to the function here. My bad. Right here. So remember the flux f dot nds. So I need f, and I need to obviously get the y taken out. So it's going to be 5 and then x squared plus z squared. And it looks like we have a 1 there still. That's nice. And then 5xz, no changes there. And I need to dot that with n. So f dot n. So I'm going to dot these two guys. Be negative 10x x squared plus z squared plus, and then 1 times 1 is 1. And it's going to be plus 10x z squared. Ooh, I see we get a little lucky here. That's nice. Let's go ahead and distribute. You get negative 10x cubed. Take away 10x z squared plus 1 plus 10x z squared. Ah, all right, that's nice. Those cancel. Okay. So my integrand becomes negative 10x cubed plus 1. And I'll pause here to if you have any questions. Okay. Are there so far so good? Do you see what we're doing here? The idea is that we have a surface. You're supposed to find the n vectors that stick up orthogonally to that surface. They're always orthogonal. Now, meanwhile, you have vector field arrows kind of poking along. And you're trying to see how many, with the dot product, how much do they agree or disagree? If they generally agree, you have positive flow. If they generally disagree, that means they're obtuse, you have negative flow. And if, you might have a case where they cancel out and you get 0 net flow. Okay. All right, so we got to work this double integral out, and we're going to do it over this region here, and actually this region right here. And so I don't like that cube, but we can still work with it. Let's just go with it. So it's double integral negative 10x cubed plus 1 dA, and you know, I don't know what you guys are thinking, but since we've got a circle here, anybody want to go with um, polar? That's what I'm thinking. If we go polar, the bounds, well, I'll do dr d theta. I have to throw an extra r in there. R would be 0 to 2, theta would be 0 to 2 pi. It's just a circle of radius 2. I do have to take this out, and this would be r cos theta, and that's going to be cubed. It's going to look a little ugly just for a moment. I have negative 10 r cubed cos cubed theta plus the one, then the arc was actually that's a fourth now. That's r. I'm trying to see if there's a faster way to do this. It's correct. You know what? It'll work. We'll just go with it. So if I do the integral with dr, and make sure I'm not, yeah, there we go. I'll just ignore the cos cubed for a moment. And so if I integrate dr, I get negative 2. So it's going to be a fifth power. So negative 2 r to the 5. And I'll just write the cos cubed theta plus 1/2 r squared from 2 to 0. The 2, that's 32, that's negative 64 cos cubed. And then that's going to be 2. What's going to be 2? It's just plus 2, and the zeros drop out. So that's easy. Then that gets integrated with the 0 and 2 pi. Okay. And you can integrate cos cubed by borrowing a cosine and writing the sine, a cos squared is 1 minus sine squared. But I think I want to mention here, we can possibly get away with using some geometry. Let me think. Give me a moment here. From 0 to 2 pi, the cosine should have an integral of 0. I think this is going to drop out. I think what we end up getting is just 2 times 2 pi, which is 4 pi. Because the cos cubed, you can't just do 1/4 cosine to the fourth, unfortunately. You have to actually work it out. But I think it just drops out because you get 1 minus sine squared times cos. And then when you integrate that, well, you get cos minus sine squared cos. I can go ahead and do that. It turns out to be the integral, so it becomes sine theta, and then this becomes u du, so it's be 1/3 sine cubed. Yep, sure enough, when you plug in 2 pi and 0, they all drop out. All right, so your answer is 4 pi. Okay. This one is a pretty hefty one because there's some unavoidable algebra that we just have to deal with. So let me go back to the original problem here. Let's just review. So you're given a vector field, you're given a surface. The surface is written explicitly in terms of y, so that means we can use this little trick right here of finding the end vector. Okay, we were told that it's going to be oriented in the positive y direction. That means that's a 1. That means these guys have to be negative. Okay, so we just take the partial derivatives, we pop them in, we make the substitution from the original surface here. That takes out the y. We just work out a big old dot product of these two right here. We're just dotting them. And you just you have to trust the algebra. And it worked out kind of nice. We got some terms to drop out. We got negative 10x cubed plus 1. And then we just had to beat it with a stick. And it worked out. I mean, I'm not going to pretend it wasn't the most fun I've ever had. But it turned out that it seemed to work out pretty kindly in the sense that we got the zeros at the end for the trig part. I don't know. I think it worked out pretty good. What do you guys think? Have it given you a headache yet? All right.
Yeah, this one was a lot.
13.5, number 4. I think I just, no, that was 13.4, number 5. All right. Yeah, I'll tell you what. Again, I'll move this one to the side. And if you think of a follow-up question, just let me know. I'll bring it back. We have a question here for 13.5, number 4. Let's bring that up. Let me go to the screen here. Let me find it. Five and 4. Curl and divergence. Okay. Let me share. So this is the one you're asking about. Consider the vector field 9y, 9x, negative 9z. Show that f is a gradient field. That means that it is the gradient of some potential function that satisfies a certain initial condition. Generally, what you do is you show, oops, sorry about that. Let me go to the screen. So generally what you do is you show that the curl is 0. Curl is actually an extension of Green's theorem. The integrand in Green's theorem is actually 1/3 of the curl formula. Did you guys catch that when you were looking at your notes? Nx minus my is actually part of the curl formula. So I'm going to do it the old fashion. I'm just going to work it out. So we have a 3×3 determinant. We put our functions here, 9y, 9x, negative 9z. We have partial x, partial y, partial z. So when I do the first one, I get the partial of y with respect to y of negative 9z, that's 0. That's 0, so it just drops out. When I do it with j, let's see, partial of x with that guy, that's 0. They're all 0. And partial of, let's see, with respect to k, it's going to be partial of x. Okay, we get 9 minus 9, which is 0. So we get 0. Okay, that indicates that f is conservative. Now, technically, there are counterexamples, but they're very rare and they're very contrived. Generally speaking, in the cases that you'll see, if you get a curl of 0, it's a conservative field. So what we need to do is we need to figure out a vector field that generates this as its gradient. And the way I do it is I take the 3 components and I integrate them one at a time with respect to x, y, and z in order. Okay. So I take the first component with respect to x, the second component with respect to y, the third component with respect to z. And so when I integrate the first one, I get 9y with respect to x, I get 9xy. The second one, I get 9xy. The third one, I get negative 9/2 z squared. And what you do is you take the union. And I'm going to theorize that the vector field function is 9xy take away 9/2 z squared. That's what I claim is the function that generates this vector field as a gradient. In other words, the gradient of v is f. Well, we can check that real quick. Let's do it. It takes only a few moments. V sub x, well, let's see. V sub x is 9y. V sub y is 9x. v sub z, there's nothing there, that drops out, 2 comes down, negative 9z. And sure enough, that's exactly what the original vector field was. And furthermore, when you plug in 0, 0, 0, you get 0. So it also satisfies. Okay. Does that help? That was Lizzie. Lizzie, did that help you?
Yeah, so I think I was just thinking about it wrong, but when you're doing the union, you're not just adding them all together, right?
No, you don't. Yeah, you'll notice that this term appears twice, right?
Hmm.
But it's actually just appearing once because it'll
Right.
actually
Okay.
satisfy both of these when you do the gradient check.
Okay. I think that's where I was messing up. But yeah, that makes a lot more sense now.
Sure. And this little maneuver works like 99.9% of the time. And for the most of the functions that you guys encounter, um, this usually works just fine. You just generate the 3 terms, and a lot of times you actually get repeated terms, and you only need one of them. So that's why you are actually forming a union. So when you union sets, you actually ignore repeated terms. If it appears once, it's good enough.
Okay. Sounds good.
Alrighty?
Thank you.
Sure. All right. Well, that was a fun one. I think my brain is still working a little bit. I can take maybe a couple more questions. Anybody want to ask me a good one? They've all been good, actually. I need to grab some paper here. Give me a second. All right. Whew. So this is 13.3, number 11. Determine whether each of the following vector fields appears to be path independent, i.e. conservative, or path dependent, that would be not conservative. And I'm going to try a trick here. I'm going to draw a circle. Can you guys see that?
Yes, we can see it.
Yeah, I'm not. Okay, I just want to make sure you can see it. It seems that this circle, when if you go in the counterclockwise direction, it kind of like up here, it kind of works against the vector field. And it's also working against the vector field down here. It's always working against the vector field. Do you notice that on this one? So it seems that when in a conservative vector field, you're gonna anytime you draw, okay, in a conservative vector field, anytime you have a closed loop, you'll always get a zero net work. And I don't think that's going to happen here because in this case, we're going against and against. We're not getting any canceling out. So this one appears to be a no. Okay. Now, on the other hand, let's do a circle. So why not? Circles are fun. It's kind of tricky to them. All right, let's do, again, I'll put a little arrow on. This one actually looks potentially conservative because if you look over here on the left side, it seems that the vector field arrows are pointing to the left, and on the right side, they're pointing to the right. And it seems like that, for instance, down in this region at the bottom, you'll have little parts that'll have non-zero work, but it looks like they cancel each other out. So in other words, like down here, this little bit right here will cancel out this little bit right here because the way the arrows are oriented. You see that symmetry? So this one, I bet you is going to be a yes. Okay. And again, we can only make educated guesses here. Let's try this one. And again, I'll draw another circle. I think this one has kind of the same sort of feature over here. It looks like they there's symmetry, and it seems like they're going to cancel each other out. I'll bet you this one's also a yes. Now, I may be wrong, but it seems right. In fact, you know what? I'm going to put a little tiny circle over here. Okay. We could probably argue that as I traverse this circle, I start up here and I go kind of counterclockwise to the left at first. Um, as I go down, like the first half, I'm going with the vector field, but then in the last half, I'm going against the vector field by symmetry. So it looks like everything's going to cancel out. So yeah, this looks like a yes as well. All right, let's do a couple more. Um, this one's kind of an odd one. I would probably say no on this one. Because again, I'm looking for that symmetry. And this is not quite symmetrical. There's if I look at like this little portion here versus this little portion here, I don't think they cancel out. My feeling is this one's a no. Constant vector fields, this is a constant vector field. This is a definite yes. Constant vector fields are always conservative. And I mean, I could draw any old closed loop. It's always, you'll have cancellation all throughout the loop. And this last guy is going to be pretty easy as well, because this one we have there's actually a definite curl in the vector field. And if I draw my arrow this way, you'll notice, oops, I didn't do that. You'll notice that I'm always going against the flow. So this one's definitely not going to have a zero net flow. It's actually going to have negative flow. So this one is a big fat no. I forgot who asked this question. Does this help? All right. Um, Ross, I think this was yours. Does this help you?
Yes, it did. Thank you.
Yeah. Again, I hope my explanations are making sense. This is one of those things where, and even as I look at these, I mean, the only one I know for certain would be like the last two. The last two I'm 100% confident on. The first four I'm like 95% confident on. The only one that I was kind of wondering about was the lower left one. But I'm pretty sure this is going to be a no. All right. How do I do that? All right, let me stop the share. All right, okay. Um, we got a couple more minutes. Any last ones?
Can we do 13.2 number 11 because it's very similar to the one you just did.
Yeah, let me go find it. 13.2, number 11. Oh, darn it. Line and rolls, 13.2, number 11. All right, yeah, we got pictures. I like pictures. All right, so let's bring that up. Determine whether the line integral of each vector field in blue along the oriented path in red is positive, negative, or zero. So you're looking for, do the blue arrows generally work with the red arrows or against or zero, or do we have like equal parts canceling? And so again, let me bring up my little annotator. On the first one, as I go this way, it looks like the vector field arrows are all orthogonal. So this one's probably zero. If I go this way, this one's the same thing. They're all orthogonal. So I bet you this one's zero. However, if I go this way, I'm going against the arrows, aren't I? So this one's going to be negative. And I think the net case over here is going to be a negative. Does that make sense?
Yes.
On this one here in the middle, top middle, we actually have symmetry. And so, for example, this bottom, compare the bottom to the top, and you'll notice that they're completely symmetrical. So I'll bet you they cancel out. The right and the left look like they cancel out. So this one looks like a 0. For the third one on the right here, we've got strong blue arrows. They're big up here, they're small down here. They're generally working with the direction of the path. So it looks like it's going to be plus here. Now down here it's going to be negative because we're kind of going against the path of the vector field arrows. But notice that these are stronger. These are bigger blue arrows. So I think we have a net 0, net positive. Okay, we'll just finish this one off. Let's see. Let's look at this guy here. I'll pick a starting point as I go. Yeah, I'm going with the vector field, but not very strongly. I mean, it's going with, but the vector field arrows are pretty weak. The two parts here, this linear part, this linear part are both orthogonal to the vector field, so these are going to both be 0. That's supposed to be the 0. Let me try that again. This one's probably going to be plus, but not very strong. Now, this outer path, it's a long path and it's going against the headwinds. So this one's like a strong negative. So net, this one's going to be a pretty strong negative. So we have a little bit of positive, a couple zeros. This one's going to be a net negative. For this one, middle, it looks like they're going to be orthogonal. Yeah, it's going to be 0 along this little bit right here. This one right here is a little, yeah, it looks orthogonal. This one I'm not feeling 100% comfortable on, but yeah, I'm gonna say 0 probably.
Yeah, that one's 0.
Okay, yeah, that one's the only one that I'm not feeling tremendously confident about. And then let's look at this last one. This is interesting. Notice that these two linear paths, this little linear path here goes with the vector field. This one actually goes against. So the two linear paths cancel. Meanwhile, the curved paths are all orthogonal. Do you all see that? So in that case, we're going to get zeros along the curved paths. And these two guys are going to cancel anyway. So this one's probably a 0. Okay, does that help?
That was extremely helpful. Thank you.
Sure. All right. Well, guys, it's a couple minutes to 7 o'clock. I'm going to go ahead and end the festivities. Um, I'll post this on my website here in a little bit if you want to look at it, on your own time. So good luck. I'm probably going to do another session on Monday. That way we'll have like time for last minute questions. Okay, so just kind of check your emails. All right, y'all. Have a good couple days. All right, 4, 3, 2, 1. Bye bye.